Okay.
Hello.
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 Can you hear well what we are in the room? Yes.
Yes.
Perfect.
Hey, Philip.
Hello.
Hi.
So Luna, please let me know if you guys are ready, so we can if we can start, or should we wait a little bit?
Can our students please turn on their cameras so we know that you are all there?
We are here.
Hello.
Hello.
Okay, there is a group. Okay, Susie is there. And Nada also, perfect. Are you guys ready? Perfect.
Looks good. So then, welcome everybody. My name is Andrei Chepurenko, and I'm the organizer of the Munich Robotic Enthusiasts Meetup. And today we have some kind of access to very exclusive content today. So today is a special meetup. We didn't have something like this before, and we are very proud. And I would like to say thank you to the guys from the Devanter company, in particular Alona and Rafael, for approaching us, for letting us also show this kind of event. And of course, I would like to say thank you to all the guys who will be presenting today. This is an amazing achievement. Even the pictures are really impressive. So I'm really excited to to see it live. And so I wish you all the success. Don't worry, everything will be good. And that's it with the introduction. So now I would like to give the word to Rafael and Aruna, and they will continue to moderate the evening. And once again, thank you very much to everybody for making this possible.
Well, the thanks is very much on our side. Thank you so much for actually hosting us and having the Roboy finals being visible to more than just our internal team. I'm really happy to see that there's more and more people joining. So to give you a quick overview for those who haven't heard about Roboy before, I will give you a very brief overview over what we are doing and who we are and so you have an idea of what you're seeing tonight. But the main sort of focus lies on the two presentations from our two student teams, and of course the live demos, because robotics is only real when it's being done live. And of course, as always with live demos, they're live, so who knows? But I'm quite confident that we'll see something pretty amazing. With that, let me quickly share my screen. So, okay, so now I have my first issue. Which all right, so you should see my slides. Do you?
Yes, yes.
Perfect. Okay, thank you so much. All right, so Roboy basically is there to solve one very big vision eventually, and that is basically creating robots that are just as good as the human body, so we can all be living in the year 2500 and stay curious indefinitely and explore the world and live on Mars and just keep on being and exploring the world. And in doing so, we're following sort of a three-step vision. And what we've been doing for the last 7 years is building musculoskeletal modular robots. It all started in 2013 with this beautiful robot. And we very quickly realized that having a student team that works on the more prototypical and outreachy things that where it's not that clear how they will be doing. I will say very useful things. So over time, in 2018, we had our first sort of Munich-built humanoid robot, which is Roboy 2.0, which we then sort of taught how to drive the rickshaw. And of course, if you have a robot that can drive the rickshaw, it has to serve ice cream. Now, what we're doing now and where we're going towards in the future, it's really about telepresence. So we finished the third generation of the Roboy 3.0 early last year, about a year ago, and then we used time from then on creating a telepresence stack. And telepresence mean becoming the robot, and you'll see this later today. Your head basically moves as the robot's head moves. You see what the robot sees, you hear what it hears, you feel what it feels, and you interact with the world as the robot, because the robot basically imitates all your emotions. And let me give you a very brief look at how this looks like. This is from our submission for a competition we're working on. So I'm here in the background, controlling the robot, and you see how the robot sort of imitating my motion. And I just grabbed this cup here, and I'm driving the wheelchair with my controller, and I'm handing over the cup to Luis, who's standing here. And what you're seeing down here is sort of my perspective, what I'm seeing in my headset, and you can really sort of see the remote world. You can talk through the robot. And that's special about Roboy. It's a musculoskeletal robot, so that it's very compliant and safe to interact with. So you get this very natural handshake. We are doing this also as part of the largest humanoid robotics competition in the world. It's called the ANA Avatar X Prize. It has a 10 million US dollar prize purse, and we are the only one, like there's only 2 German-speaking teams left. And it's basically about solving exactly what you've seen, basically teleporting the presence of a person somewhere else. And I'll have a very quick video so you get a feeling for this competition and why it's amazing to be part of it.
We had internet, we had iPhones, now we'll have avatars.
The ANA Avatar X Prize is a $10 million competition that challenges teams to develop a physical robotic avatar system that can transport your senses, actions, and presence to a remote location in real time and feel as if you're actually there.
We'll be able to completely break through all of the barriers of distance, time, and cultures that exist in our world. I think that will allow us to unleash the full potential of humanity for the very first time.
Yes, so that's why we're really excited, because this is really a competition made for Roboy. If you want to become a robot, the first step is sort of teleporting into one. And one very important aspect of the Roboy world is our student teams. So while they by now have turned into a research lab that is independent and is incorporated as a not-for-profit entity, we still have student teams every semester, and we're actually growing these student teams starting from TU Munich, which is sort of our home university. We have collaboration with Zurich, with Ghent universities and others. Basically giving the students the possibility to work with real hardware, to spend a semester and to learn how to interdisciplinary develop robotics, and also how to collaborate between the teams, because that is also a very important aspect in robotics, because you always have complex mechatronics setups. And that's basically already it. This is the goal. I would like to really quickly thanks to all our partners which are supporting us. There's the best university in the world. It's a number of very big companies that are supporting us and making this possible. And with that, I really want to give over to our first student team. I hope you guys are ready. So the first student team will be demonstrating the construct, and I will just ask you to start sharing your screen and starting your presentation.
Of course. Are you guys ready?
Yep.
Yes. Okay. Let me just do this again to have audio as well. Okay. Hello, everybody, and thank you for joining us today on our final presentation. We team consisting of Selim, Philip, and me, Furka. We have worked a total of 6 months on this term's Roboy student team. We will first show you a video that we have created back in the beginning of this term, where we have taken on these tasks and where we should envision what we would have done by the end of this term. So I'll just start and you enjoy.
Oh, yes, this is going to look. Ow! Guys, we really have to do something about the slapping problem.
And after hours and hours of coding, testing, and debugging, our brave students came up with an idea. A training world where Roboy is mirroring every move you make. With this procedure, the operator not only gets used to the UI, but also learns Roboy's capabilities and limitations. Finally, after going through this learning process, the operator is now able to give others a high five from anywhere in the world. So this was our initial tasks, let's call them. And let's switch slides and get to here. So we have divided our initial task into 4 different subgroups consisting of the operator interface, where we basically plan to getting functionality to some widgets that are already on the interface, then to remove some widgets and add more widgets as we. Our next step was to do a tutorial that basically explains the user on how to interact with the operator user interface and how to control Roboy. Our next task was real visual. We want to have pictures for the operator to have a more fluent interaction to Roboy. Then our initial last task was to do work on the controls of Roboy. Let's see how we have managed to work on these tasks. Let's again start with the operator user interface. You can see that we have actually worked on this task. We have now an operator user interface with widgets. Then we have worked on a prototype for training the operator.
Weil seine PU anscheinend damit involviert ist und zuständig ist.
The next step would then be to implement the stereo vision for the robot, which we have also done. Then our initial last task would have been the control of robot. Here you can see a handshake. But as always, you initially plan to do something, but in the end, it turns out to be more work. So we have also worked on an interface for the Exoforce team, which works on the caged operators in. We will hear more about this from our next team. Let's have a look into these 4 tasks. Our first task was the operator user interface. You can see here that we have widgets on the top, which we call the system status widgets. The operator is able to interact with these widgets to check modalities or to check connections. On the bottom left, you can see the body part status. This allows the operator to see how the body is doing. On the bottom right, you can see an emotion widget. We are now going to be going more detail into what these widgets do.
Okay, so let me start with the system status widgets. So the first one is a display setup. So each operator, each user has a different distance between his or her eyes. So this interpupillary distance has to be accounted, but the cameras in the robot are always at the same position. So we address this issue software-wise, and we can position the displays at the VR screen to different positions so that the user always has a comfortable 3D vision. So next we have the widgets for sound and from microphone, which just allow to mute robot sound and to mute yourself. Then we have the head control, which allows to control if you want to currently control Roboy's head or if you currently don't want to control it. Then we have the network widget, which gives a few informations about the connection to the robot. And we have the cage status, which gives a few informations about the status of the cage if it's initialized.
Then let's get to the body start widgets. We have 3 different states, starting with the red one. This one stands for a problem with the motor in itself for each specific body part. The color yellow stands for no connection to this body part. And the color green stands for a connection and the problem and the motor giving no problem. In addition to this, you can see 2 more states, which are black and white highlighted. This is another functionality that we've added on. So you can see everything is highlighted except for the hand and the right arm. This allows the operator to disable the control of these parts. Now our Roboy would only control the movement of the operator's hand, his left body part, his left hand, and the wheelchair, and would then ignore the movement of the right arm. Allows the user to do something in real without Roboy actually copying this move. Then we have an emotion widget, which is on the bottom right. The operator is able to choose from a variety of emotions. These are shown down here. There are emotions like smiling, laughing, and being shy. This is as the operator is controlling Roboy, he's not actually able to see himself and to be able to see what emotion he's currently showing. We've needed a widget that actually shows that status.
Right, so now onto the trainings world. We had previously planned multiple scenes for different training purposes, as in a scene to teach the user how to use the controller, a scene to teach the user how to interact with the HUD, and a scene to teach the user to steer and operate Roboy. But we came up with a better solution. As you can see here, we just made an all-in-one training scene in which the user at the same time learns about the controller, different buttons, and can learn to steer and operate Roboy. As for the interaction with the HUD widgets, we made those explanations optional and available all throughout the experience, whether it's a training or not. So we can see here that's the middle widget. That's the one that enables or disables the descriptive disk. And case in point, we can see in this slide that you're interacting with the sound widget and you have an explanation. In the next slide as well, we can see that we get an explanation. And when we deactivate it, as shown in this slide, we can see that we don't have explanations anymore. So the user can activate when he forgets something and deactivate when he doesn't need explanation.
Okay, so now let me go a bit deeper into how the training looks now after we implemented it. So first up, you are now in a trainings room and in front of you is a mirror. So this mirror helps you to understand what you, or better, the robot you are controlling is currently doing. So we have a simulation in there, and you can control the simulation that will mimic your movement. So first up, you can train the head control, and you can see that the robot's head is following. Then next up, we have arm control. And there you can train controlling the arms of the robot and the hands. We have wheelchair control, where you can drive a bit around in the simulation. And last, if you are done, if you've learned how to control the simulated Roboy, you can then go through a portal to the real Roboy, where you can then control the real robot. So what can you all control? So it's possible to control the movement of the arms, and it's possible to open and close the hands. This is all independent of each other, so you can either only control one arm or only the other, only control one hand. Then it's also possible to control the head or to disable it. And the status widget will always show you which parts are currently active. And last, we have the 3D vision, which is showing two correctly aligned pictures from both cameras for both eyes. And that's how we control Roboy. Then we have the cage interface to the other team. They will tell you more about the cage itself, but for the interface, we are sending the initialize and the stop message. And if the cage is currently initialized, we are sending the controller pose to the cage so that the cage knows where the hands of the user, of the operator are. And we are forwarding data from the robot, for example, collision data, to the cage. So how does this interface work? On the left side, we see Roboy or the simulation, and this can be anywhere in the world. And to connect to Roboy, we use Animus, a tool from CyberSelf that allows to send data globally. And this way, we can connect Roboy or the simulation to our Teleport app, which we developed. And from there, we can delegate information on and also send other information using Ross Sharp on the Teleport app side and Rust on the Exoforce side to send the information to the other team. So now let's look at this in a bit more detail. So on the left side, we see that we can either communicate with a PyBullet simulation or we communicate with Roboy, and this happens locally using ROS. Then we give the information to Animus, and using Animus, we can globally transmit it to our Teleport app. Then this is where the operator is. This runs on the headset of the operator. It's a Teleport app with a HUD and with a trainings world, and both scenes are able to communicate with Roboy and also with a cage. And to communicate with a cage, we use Ross Sharp on the Teleport side, because Unity is using, we are using Unity. Unity is using C#, and Ross Sharp allows to run Ross in C#. And then we send the information over, and cage then can receive them and process the data. Okay, so what special features do we have that we didn't mention yet? So first up, we made the hardware packages modular. So there are different hardwares that can be used. For example, sense gloves, they are some kind of haptic gloves, which can be activated and can be used, but you don't want to use them all the time. So they can also be removed from the project without any problem. And we used Unity XR interaction with this new tool from Unity. And it allows to be platform independent, which means that we can connect to almost any virtual reality headset and can easily switch between headsets. Okay, so let's finally look at what we learned in all this process. So first we learned how to use the Unity engine. So 2 of our 3 team members didn't have any experience with Unity before this semester, and now they have. Second, we learned how to use ROS and how to interface with it. We were also working with Docker, so now we know a bit more about Docker, how it's working. And for programming languages, we used C# mostly, and also a bit Python, so we also learned a bit about this. And then for the soft skills, yeah, we learned that we should use newer Unity versions when we are using new plugins, because new plugins can fix things that can break things. And new Unity versions allow to get these new plugin versions. Then we learned that we should ask precise questions. It makes your life easier and leads to less misunderstandings. Then we learned to not stick to any blockers that are blocking our way, but to look for a way around them. And lastly, from the other team, we learned, do not break it. And then there's one thing we learned today again. Nothing was working anymore 3 hours before the demo. Just restart the computer or the Unity or the application. It always helps. Okay.
So part of our task was to also do a final video. It quite nicely connects to our initial vision video, and will now show you what we have accomplished. So let's start.
Guys, we really have to do something about the slapping problem.
But things don't always go as planned.
Oh shit, here we go again.
So just do it! Make your dreams come true!
So we did. We have created this construct app that is connected to the Animus server, which connects us to these modalities as well as the connection to the Yes, this may also back to our initial. Sounds complex? Well, actually it's not. Put on the headset, go through the training, have a look into the mirror, look at the status widgets, look at the emotion widget, look at the body widget, immersively transition into Roboy, control Roboy anywhere in the world, give your friend a high five, succeed in life, change the world. Thank you.
So this was our final video, and let's go here. Thank you for listening. If you have any questions, we are ready to answer them.
So if you have any questions, just unmute yourself and yeah, ask ahead.
So guys, could you please say a couple of more words about this Animus server, what it is? Is it a library for real-time communication, or what exactly it is?
So we can use the Animus server. Basically, it's a server that's running stuff like the PyBullet or the simulation. And we use it as a communication way to get basically ROS messages onto our Unity app. This is not done via ROS, but the Animus SDK. So we package them into arrays, get the data, then revert them to ROS messages again, and then send them over to the cage. So it's a server that we are using.
So maybe one word about it. It's a collaboration with a UK startup called CyberSelves. We're using their sort of telepresence tech, and it takes care, like Animus, sort of as a concept, it takes care of all the data transmission between the operator side and the robot side.
I see. Thank you.
Any other questions?
Yeah, I would like to ask about the latency. Raphael, you have mentioned something about working with a robot on Mars.
Yeah.
How would you overcome the latency I know about light, speed of light and ultrasonic.
Yeah, no, it's a very good question. So on Mars, obviously you wouldn't when you have on average 8 minutes latency to Mars. But there the idea is more like once we have first habitats on Mars, it's obviously a lot easier to send a robot into the near vacuum, sandy plains than actually making sure a human survives out there. So the idea is that most sort of works outside of the habitats will be done through robots, which are teleoperated by the crew that is already on Mars or living there. And then the current latency right now, so this is of course strongly network dependent. We are around 200 milliseconds and pushing it downwards. Of course, we're also talking to a lot of telco providers as partners to make sure that eventually we can get below 100 milliseconds, definitely, ideally towards like 60 or 50 milliseconds. So it really feels like instant. And if you're a gamer, you know that you need less than like 30 milliseconds to have a good ping.
Absolutely.
And that's exactly the same.
Yeah. And my last question is about the hit when the robot wanted to make the high five. How did you overcome that? I mean, was it a latency issue or was it a processing issue?
So there are more problems onto this. So basically, there are more like that's the one thing is the latency. The other part is how the operator actually knows how to control Roboy. This we overcome with the trainings world. Now we have the functionality that the operator is able to detach control of some body parts. And these all stuff works together to ensure that the operator knows how to give a high five. And we will soon show you hopefully a handshake done with the actual robot. And we are working on that right now.
Yeah.
I also have a question. Speaking about latency, are you guys doing any kind of adaptation so if the network conditions are changed? Are you doing some counter measurements like, I don't know, reducing frame rate or reducing the sampling frequency just to ensure that you can still be able to communicate over the degraded connection, for example?
So maybe that's again. So since, as I said, we're using sort of this transmission package from the startup. As of right now, there is no automatic modality degrading or anything like that. But this is something they're working on. And another thing that we did in the past in this direction was that we did a master thesis where we have been looking into slowly increasing latency in a simulation environment. So like you're in VR, but the latency of you controlling your robot is increasing. And then when you switch over to sort of the latency into the actual robot, you're already sort of kind of used to this latency. And this way, you can show that the embodiment is actually greater or better, although the latency is high. That's a way of sort of easing into the latency. It's like a cognitive trick. We've been doing some evaluations in this direction as a trick, but it's not like live right now.
I see. Makes sense. Thank you.
So we will be ready to show you live demo and fingers crossed it works. Can you guys hear me well and see the Roboy and the Philip?
Yes.
Yes.
Perfect. So yeah, this is Philip who was just giving a presentation. And this is beautiful Roboy 3.0, freshly baked from October. And here I have the view of what Philip sees from the Oculus. So now Philip is gonna comment for you what's happening.
Okay, so can you hear me?
Yes.
Okay, very nice. So first here I am in the training hall, and you see in front of me is a mirror I already told you about. So here I can move the head, I can move my hand if I want to. So let's move them a bit around. I can also close my hands. And finally, let's move around the wheelchair, because then we can get the portal to the real robot. So here you can see what the real robot is currently seeing. And maybe before we go into there, let's take a little look at the widgets first. So up here, I hope you can see the widgets.
Yes.
Yes.
I have, for example, the connection. It tells me that it has a certain amount of frames per second. It's varying a bit. So then I have the mute and silence widgets, but I don't have the audition modality currently on as Roboy is sitting next to me. And you also see the other widgets up there. For example, I can show you this one later. So maybe let's now move into the robot. Here I am. And yeah, now I'm seeing what the robot is seeing, and I can still move the head around. And now you see which parts of the robot are currently active and which ones are not active. And also I can now show you this widget, where I can, for example, move the image a bit further away from me to see more of it. Okay, so now let's come to the funny part, to controlling Roboy. So if I look a bit down, then I see the robot arm. Now let's move up the right arm. And Elona, do you want a handshake?
Yes, yes, yes. I'm coming for the handshake. Through you, all of you.
Great.
Let's do a handshake. Very nice. Very nice.
Do you also want to give me a fist?
Let's just fist bump. Almost.
Now finally, give me a rubber.
Okay, I do. Can you go down a bit with your arm?
Yes.
Okay, let's try to do this. Can you try to get it?
Let's see. Almost.
Okay. Here you go.
I have it. And
Do you know what it is? Do you know what it is you're holding?
the rubber duck.
Okay, yes.
So now let's send it flying. I love setting ducks, rubber ducks flying. Okay, so now before we finish, let's get it back to the initial position.
And the emotions.
And look at the emotions, right? So let's predict what your day will be bringing you today. So, Roboy, what do you say? Ooh, you will be good. You get rich today. Something more? Ooh, seems like you have a good love life. Have fun, guys.
I guess that was the demo of the construct team. And Philip now just exited the robot and he can move and the robot is not moving. So thanks.
Very, very cool. Perfect. Thank you so much. Is there any questions directly about the demo, which I have to say was very smooth. I'm super excited, especially since I'm like a lot far away. I had no way of interacting with it. So I love to see that it was just so, it went so perfect. Makes me really proud. So you have any questions about it, or should we move on to the next team?
I have a question.
Yes.
How was the feeling of the rubber duck? How was the feedback as a controller? Could you give some intuition about it?
So right now we do not give any feedback on haptics, so you don't feel how much pressure you're applying. This is so right now we use this relatively simplified control with the controllers. We do have a setup where we have the sense gloves that actually can create feedback, but these hands we have right now, they don't actually provide any kind of force feedback. So this is like future research and future things we work on. But it's very high on our priority list because haptics is actually very important for teleoperation or for efficient teleoperation. You can do a lot of things just with vision, visual servoing, but it gets a lot more efficient once you have haptics.
Cool, thank you.
Perfect. So then I would suggest we move to the second team. Exoforce, are you ready? You want to take your screen?
Yes, we are. Okay, do you see it?
Yes, perfect. Thank you.
1 second. Okay. So hello again. Welcome everyone. We are Exoforce control team. This is Manuel, this is Susie, and I'm Nada. And this is our final presentation for Roboy practical course. So let's start with a little overview. What is Exoforce? Exoforce is a full body force feedback robot. Now, what does that mean? Well, it's a cage that can replicate forces from VR or remote robotic avatar. So you step into the cage on this catwalk mini omnidirectional treadmill and wear the suit where the tendons are attached, and you can control Roboy as usual. When Roboy collides into something or catches something, like for example here, the tendons are going to replicate that force on your body. So you actually feel the collision. This project was actually already started last semester, so we are building upon this system and improving it, hopefully. As you can see, the force feedback is not full body yet. For now, it's the hands of the operator we're focusing on. Yeah, what we planned for this semester is summarized in this vision video. Let's watch. I cannot click it somehow. Guys, you didn't share a sound. We don't have sound. How can I do that?
You have to restart your screen sharing in Zoom because you didn't put the checkbox on share audio. So there's like 2 small checkboxes below, and both need to be checked, and then it's optimized for audio streaming and video streaming.
Can you see this?
Yes, now we can see the screen.
Okay.
Today is the first day that I
now we
connect
also
myself to Roboy on the Mars. Theoretically, I can see everything in this VR glasses what he sees. Let's connect. Oh, hi, Roboy.
I do what you do.
Really?
Can you see what I see?
Look, 2 ones.
Hey, doctor.
What happened?
My operator just broke my arm.
Poor you. You need a better telepresence system.
Hey, Roboy, we can help you.
We are gonna add a position control, so the movements of the operator are limited by the ones you are able to do.
We are also adding force control to the cage, so the operator can have a more precise experience feeling the work you perceive.
Hi, Roboy. Glad to see you again. Oh, wait, look, what's that? The new Tesla model. What happened? Oops, I did it again.
Yes, we now have an improved telepresence system.
Hello, can you see the screen?
Yes.
Okay.
So you're creating an echo.
Okay. Here?
No, you're still creating an echo. You wait. But now I muted you. Wait. Where are you? Where are you? Where are you?
Is it better?
No, you have to turn off the sound of the other PC. Like the one that is sharing. You need to turn off its sound, and it's so otherwise it's creating a loop.
Okay, now?
Still.
How do I do this? Can you hear us now?
Yeah, do you have the sound on? Like, can you just turn off like the sound so you don't hear me talking? Then there's also no echo.
Okay, now?
Still.
I don't understand where this is. Can you exit all of the Zoom devices that are in the room except for the PC, or it's not possible? Or mute them?
No, it's better?
No.
No.
Share your second PC without sound until you have a video again, and I think that should be fine.
Okay, so we're gonna switch to the other PC.
You could just restart sharing without the audio stream.
Yes. Muted. Hello.
Are you sharing screen?
I'm going to share screen. So maybe yeah. Okay.
Okay, looks good now. Are you talking? We can't hear you though.
Okay.
Oh, now we can hear you.
Sorry about
Okay. Perfect.
Okay. Sorry, really sorry about this. Let's get a bit into detail. So what we planned for the semester. So the system that we inherited actually applies forces onto the end effectors of the operator, but we had no means of knowing how much force we are actually applying. So our main task in the semester is to actually measure and control the forces that we're applying, and that is our first feature, force control. Our second feature is a lock and on collision. That means, so if Roboy can't move, operator also can't move. And yeah, for this feature, we have two scenarios. So this happens if Roboy, for example, collides into an immobile object, or if he tries to reach a position that he physically cannot reach. Okay, for cage optimization, this is a task that we wanted to do to improve the cage that we had. So this cage had some shortcomings. It, for example, needed too much time for setup. It also had this problem where the tendons went out of the pulleys and the winches, which was annoying for everybody, for the operator. So yeah, we tried to solve this problem and planned to solve this problem. Yeah, and we need to communicate with the other team to have this whole app that the other team presented, so that the operator sees this cool stuff in the cage.
And what we accomplished. Our main task is force control, which is our priority number 1. That is done successfully. And however, locking and collision is postponed due to time constraints. The cage optimization and communication interface were also done.
Okay, so let's go a bit into more detail on what we actually implemented. So the Exoforce system needs to communicate with 2 main components. On one side, we have the actual physical cage. As we've shown before, inside the cage, we have this person connected to the tendons and the motors. And the Exoforce system needs to change the position and apply forces to this motor so the actual person can feel that. On the other side, we have the TeleportVR app. As the other team already explained, this is the app that is going to communicate with the actual robot or the simulation. From this app, we need 2 pieces of information. The first one is the collision that happens in the robot. This has information about where it happened, the direction, and the amount of force. And the second piece of information is where the hands of the operator are inside the cage. Using this information, the Exoforce needs to perform a force decomposition. What we mean with this is in the cage, we have a number of tendons connected to each one of the hands. That means that we cannot apply force in any direction, just in the direction of the tendons. So if, for example, we want to apply a force downwards, we need to actually decompose this force and find the force, the amount of force we need to apply to each tendon so we can replicate the force that happened on the robot. After doing this force decomposition, we actually want to apply this force to each individual tendon. For that, we have a force control node. This is going to receive the target force for each one of the tendons and make sure that it's actually being applied the way we want it to. Now to go a bit into detail on the force control, Susie is going to talk about the sensors.
Okay, so first we have to choose a sensor, and we did a lot of research. The load cells have 4 types that we can choose. They have different accuracy and sensitivity. The first one, the capacity, it measures the capacitate and between 2 plates. The strain gauge is actually a transducer that changes in electrical resistance under stress or strain. And the last 2 ones, pneumatic and hydraulic, as said in their names, they are filled with gas or fluid and measures the pressure. They can be made as soft sensors. Actually, we considered that, but however, the accuracy and sensitivity won't be enough for us. So we went for the strain gauge one that is the most popular one on the market. We also had some other requirements, that is, it should be the tension load cell, should be pulled, not pressed, and the resolution should be low enough, at least lower than 1 Newton. And based on our test scenario, we need the maximum force 100 Newton, corresponds 10 kilos. The sensors we prefer to be miniature and lightweight, so its size and weight won't influence the test results too much. We also wished a fair price. So we chose called DYLY 108, and we bought 20 of them, 8 sensors on each, as you can see here, on each wrist, and 1 on the back, 3 as backup. To interpret and analyze the sensor signals, we need the load cell amplifiers. So we wished it can have some easy interface that we can start maybe out of box. To have that on our computer, we need the USB connection, and we also wished for the open source libraries that can be done on cross-platform and in multiple versions of different languages. So the model we chose is called Phagic Bridge for input. That 1 amplifier can connect 4 sensors, and we put them on the back of the treadmill that hopefully you'll see later in the demo.
So now a bit more of the design of the force control. As we mentioned, we have a cage, and this cage has motors, and we need to apply a force to these motors. The way we're doing that is with an FPGA board. This board is running a ROS node called the Roboy plexus, and this one is sending a set point of a PWM value for the motors. This way we can increase the force apply or decrease the force apply. And this is the setup we had last semester, and we actually don't know how much force we apply. Like, we can increase it, but this is not accurate. So as Susie mentioned, this semester we bought the sensors, and we have connected 1 sensors to each one of the tendons, so we can actually measure how much force we apply. With this information, we implemented a force control node that is going to take the actual force that it's being applied and the target force that we want to apply and actually control the force on each one of the tendons. We're running 1 PID controller for each motor on the cage. And one important decision we had to make was, first, we wanted to run this node also on the FPGA board, but the moment we tried that, the computing power of the board was not enough. So when we run 16 PIDs simultaneously, the frequency of the control loop dropped too much, and we actually were not able to control it the way we wanted to. So we decided to run this node on a different PC, and these two are communicating through those topics, actually through the network, but we got good enough results doing it this way. After the implementation, we actually had to tune the PID controller. We can see on this graph the result after our tuning. The first thing we can see is this peak, which is not a normal sinusoidal peak. The explanation we found for this is that we actually want to apply a force to a tendon. So we can only pull on one side, but if we want to release, we can actually not push the tendon. So the moment we start releasing the force, the elasticity of the tendon just drops the force, and that's why we see this weird behavior. We also see a second weird peak on the graph. We actually are not sure what this is happening. We think this is about the sensors and the way we're reading the values, but because of time constraints, we were not able to actually keep debugging. Even though we have this weird behavior, we can see how we actually achieve the target force we want. Our second test we performed was actually sending a sinusoidal target force, and we can see how actually the PID is not the best, but it tries to follow the target force. So of course, the control has a lot of room for improvement, but we decided that as a first step, this was actually good enough to keep working on this and actually apply collisions to the operator in the cage.
Okay, to do all these tests, we of course need our cage. The cage is mainly built from last semester, as we mentioned, and there are two issues left over as Nada did in the introduction. The first one is the tendons keeps going out of the winches and the pulleys. And so we had this 3D printed clip on the winch and also formed a motor glue on the pulley. When it dries, it keeps in the form and is still elastic. And that did a good job, actually. The second issue was the setup time takes too long. And so we hoped for that we replaced the wrist attachment, which was 3D printed, to a much more comfortable one that is a nylon watch strap. And it has some metal rings on it. There, the tendons and sensors can be connected to. So let's go to the interface.
Yeah, so we said we need to integrate both teams and to integrate both projects. So we need to specify how the interface is going to be. So as we inherited this system, that already worked, we already know which information we need from the other components. From the Roboy, we need information about collision and information about body information, which is some dimensions about the links, initial pauses and such. And we need from the headset the end effector pauses as well as some initialization information. We also need to know when the operator is ready to start the cage and when he wants to stop it. Of course, the components would not always run on the same environments. Yeah, that's the main point of telepresence, right? So yeah, interfacing becomes a little more complicated. Yeah, with the headset, we have no problem actually, because the headset and the cage would normally run on the same network, but Roboy can be on Mars, as we already mentioned. So we need something to interact with him, and that something is Animus that the other team already mentioned. We communicate through this collision modality. Yeah, so the system is a bit heterogeneous, a lot heterogeneous, and components run on different technologies. So Roboy and Animus run on ROS1, and they interact through ROS. The Construct app runs on Unity. We're using ROS Sharp and communicates with Animus through Animus SDK. And Exoforce runs on ROS2 and communicates with Construct through a ROS bridge. Yeah, so this ROS bridge is ROS2 web bridge, and actually it created one problem for us, which is that sometimes both versions did not have the same definitions of the messages. For example, the header message. And yeah, this ROS bridge did not handle that, so we needed to adapt and then change those messages and use other ones. Also, we had this problem with ROS Sharp that we weren't sure if it actually worked with services. So what we did is we used 2 topics for each service, one for request and one for response. Yeah, so test results. For force control, we sent a force to one motor and measured the force applied, and the error was 90% of the time less than 1 Newton, which is good. But we noticed that when the force is too high, we actually, we noticed that when the target is too high, the settling time is actually, it takes more time to settle the value. So we have more oscillations. So we think that's a PID problem, of course, and we think, that is room for improvement. An operator can differentiate between 3 different weights, 7 times out of 10. And here the forces that we send need to be decomposable. Decomposition that Manuel already talked about, because if not, then this force does not reach the cage. Yeah, for cage optimization, we tested for 10 minutes straight, and the winches and pulleys, the tendons did not slip off the winches and pulleys much. It was like maximum 2 times. So this is also a big improvement compared to last semester. The problem is for the setup time, it wasn't really less than, it was a bit less than last semester, but we reached for 60 seconds, and this was not possible. The communication interface was successfully tested. So we get, the operator can initialize the cage, the operator can start and stop the cage on demand, and the collisions are being sent and received successfully.
Okay, after 1 semester long hard working together, our team learned a lot of ROS versions and how the load cell works, how we calibrate them, how we tune the PID, as you have already seen. Also, we learned a little bit how we can improve the 3D printing results, not only in the 3D printer settings, but also like CAD models can be also improved. And the most important one is ask a lot and offer help as fast as possible. So we communicate a lot, and that's how we get the problem solved and things done easier and faster. Okay, here's our final result. Please enjoy. I hope I can get it full screen. Can you guys hear the audio this time?
Yes, it works nicely.
Okay, I have to quit and enter again to enter the full screen. Just 1 moment. Yeah.
You muted the sound.
We muted the sound. Sorry for that. Stop sharing. This one.
I mean, I'm talking about a revolution here.
You become Roboy.
Did you enjoy Exoforce 1.0 but still want more? More freedom, more control, more connection. Exoforce 2.0 is finally out. Do not let distance or dimension separate you.
Okay, so that was our final video. Yeah, thank you for listening, and if you have any questions, feel free to ask.
Can you guys stop sharing your screen?
Perfect. Thank you. So, questions?
I have a question. So, working with PID controllers, is the standard problem is how to define this P and PID parameters. So my question is, how do you guys, what kind of approach you were using to find the right coefficients? Any special methods or just trying? Or
well, not any specific method. Actually, we did this with graph. At the beginning, we tried like trying random values on, well, not random, but increasing values on P gain. And then using the D gain also. We're not using I gain actually. Like the output of our controller is not getting directly to the PWM set point, but we have one like PWM's variable. And the output of the PID is actually changing this output. So when there is no error, the output is 0, and we maintain one value. That's why we don't have an I gain.
Okay, thank you.
You do questions?
Mm-hmm. Any other question? If not, we can continue to the demo.
So I think, I mean, it would be good if you had some questions because the demo will take a few minutes to set up.
Okay, I have a question then.
Yep.
Sure.
I didn't understand this podest where it was looking like a walking pad with all these wires. What are the wires for? Is it the mapping of
inside the cage, you mean?
Yeah.
Yeah, so we have, the person inside has these two wrist watches on the watch wristbands on the hands. And we can connect to this one 8 tendons, like just a cable, which is connected to a motor. So by rotating the motor, we can actually apply a force to this tendon. And we have 8 on each hand, 4 on the top and 4 on the bottom. And using these tendons, we can actually apply forces to the 2 hands of the person.
And the calibration of that, is it automatic or do you manually calibrate?
Which kind of calibration you mean?
I mean the motors. When the lead is getting longer, maybe you've changed it, and then the calibration would change. I guess.
So what we do at the beginning is we apply a minimum force, 4 newtons. So the motors are always pulling, and we don't have a slack on the tendon.
All right.
One issue that we do have is the force control. Of course, if we start pulling, the force control is going to release the motor, right? But if we run out of tendon, the motor is going to start spinning on the other way, and like trying to release the force is going to start pulling. And this is one issue that we haven't solved yet. But yeah, so long as we don't run out of tendon, we always have no slack because of this force, and we can apply more forces on top of that.
Okay, thank you. My last question is, the cage looks like omnidirectional walking pad.
Yeah.
Are you intending to do something like that, or?
Eventually, when the whole system works, of course, it would be nice to walk with the robot, right? Right now, for the setup, we just have it there on the middle, and we are using it to attach some tendons right now, but not actually for walking.
All right, thanks.
But we had it. I mean, we had it already integrated in the past. It was just like that. This semester really wanted to focus on making that our sort of force display works as intended, and then bringing it back. So the main problem is you can freely walk in it, right? So you can also rotate in it, and that means you have these tendons that sort of hold you in place. But if you rotate, how do you handle this? We had ideas of rotating the whole cage with the operator, but I mean, we just decided that for the time being, we focus on building this sort of portal robot or puppeteering robot. And then once this is perfect, we can figure out how we rotate this thing with the operator.
Yeah, I have an idea, Raphael. Have you seen the Ready Player One?
Of course.
Yeah, okay.
But like, how do you want to solve? Like, what is the suggestion? Because they don't. I mean, they can just fake it.
True, but I was thinking about that the analogy between yours and.
No, it's definitely the same idea. Like, so I mean, we also have a haptic vest that allows you to sort of give like just some touch feedback in a way to the vest and to the gloves as well. Like one major aspect, right, is understanding how you interact with rigid objects in the world, and for this is something that Exoforce can do, and sort of also giving you these external forces, so you truly understand when the robot, for example, has hit the table, and you feel this physically because you can't actually move your hand further down because it's being prevented by the tendons, and this is really the idea. Making the user also feel weights and feel collisions with the environment. And then, of course, connecting this to the robot eventually. Yeah, so it's quite a complex endeavor, and I think we'll be working on this for a while to come. So this semester really was sort of about, yeah, as I said, force control, getting it integrated nicely from the setup with the. Yeah, because in the semester before, we basically built the thing, so the physical structure, and then now it's sort of iteratively improving over time.
Very interesting. Yeah, excited about the future.
Yeah, me too. Yeah, like getting proper force control is actually very hard for tendon-driven robots because you have a somewhat elastic system. Like you have some elasticity in the tendons, and you've seen it in the graphs. These oscillations, they come partially from the fact that there's some elasticity, and from this elasticity also some. It behaves very differently also because like as soon as you go towards a tendon, the force sort of drops immediately because there's no rigid connection to it. Whereas usually when you use this kind of controller, you have like a rigid connection, so the force is transmissible, which in this case it's not, at least not only in one direction, and that makes it a real pain. And this is something we're going to be working on in the future, also figuring out algorithms of how to make this more intuitive. I do believe, however, that this has a lot of potential because there's other ways of doing this, like using sort of attaching a robot to your hands, like an external robot, sort of that forces to you, and that's sort of how this is commonly done. But there, of course, you lack transparency, and when you keep the tendon slack, you can have perfect transparency. Like you don't feel anything, and then you only need to kind of make sure that once you're moving towards the surface, you have already prepared your tendons, and then sort of once you hit it, so you can really create this very shockwave-like behavior that you want to create, that gives a very crisp sort of feeling of hitting something, which is really hard to do with sort of more classical approaches. Yeah. Perfect. So if we can discuss also further on. The team alone just wrote me that they are ready. So I think we are moving on to the demo. And fingers crossed this one learns as smooth as the last one.
Okay, so can you hear me?
Yes.
Here we can see the cage that we built in Roboy Lab. First, yeah, we can see Susie inside. She has the watch wristbands, as we said. We can see the tendons connected to each one of the tendons goes to one pulley motor setup. We have 8 on each hand. One thing we can see actually is that, yeah, the tendons on the front and on the side can go to the cage, but the fourth tendon can actually not go in that direction because the operator is in it. So what we actually did is attach some tendons to the actual body. We have some tube housing and the motors are on the top. So of course, this is a solution for this issue, but this also limits the workspace in which we can actually apply a force. Like in the case, the hand is where it is right now. this tendon cannot pull in that direction downwards. So there are some forces that we can actually not decompose. Susie has already the headset on. We can see on the screen actually what she's seeing. This is something that the team already explained. On this side, we are running a Roboy simulation. Yeah. So right now we're not working with the real Roboy as before, but Susie is going to move and we're actually going to control this Roboy simulation. And in here we're going to send some boxes, object, tables, walls, so Susie can move, try to touch them, and we can see then how she actually is going to feel this force feedback. Finally, the motors, as said, are connected to this FPGA board that we have here. This one is connected to the network, and we have all the sensors on the hands are connected to the fidgets that we said that are here on the back. This one go with a USB to another PC, which is running the actual Exoforce system. So yeah, this is the setup we have this semester. Now Susie is connected to the headset and she can decide when she actually wants to start the Exoforce.
Maybe I should move my head too much.
Yeah, right now we're working on the app. We're using the Animus SDK to connect to the actual simulation. And we're also using this ROS sharp to connect to the ROS system. So we had some issues to actually build the app on the headset. So that's why we're running it on a PC with an Oculus Link.
The app is not working.
Yeah. Yes, as we can see, sometimes it crashes. So it's not only that we cannot run it on the headset, but using this setup with the Animus SDK, the ROS sharp, the app sometimes crashes. We can see now she's connected. Whenever you're ready, you can initialize. Okay. And we're gonna see how the system pulls the slack of the tendons.
Okay, 3, 2, 1, go. Okay.
So now she can move inside the cage.
And I now enter the simulation. I'm in the simulation.
So we can see how she's moving, and the simulation is actually following her. We can actually see how she in the cage is moving, and this minimal force on the tendons is actually keeping them tight. Now we are going to proceed to apply some forces. First test scenario is going to be a wall.
Okay.
So now on the simulation, she has a wall in front of her.
Okay, I see a wall on the right side in front of me, and I go back a little bit. I'm going to now touch it. There I feel this, yes, this blocking.
As we can see, the PID, of course, is not perfect, and we have some oscillation on the motors when the force is applied.
Yes.
But she can feel.
So yeah, so I know the wall is exactly this far from me. Yes.
Okay, next test scenario is going to be a table. So we can test an horizontal object.
Okay,
we place a table. Now Susie's going to touch it.
I'm going to touch it with my right hand. Yeah.
Yeah, we can see how the top tendons are getting a bit crazy.
I think Oculus Link is being able again.
Yeah, this is one of the issues of the app. We lost connection right now. We have to restart the application. Next test scenario in the simulation is going to be an object, so she can actually hold it.
Not yet. I enter the simulation again.
You have to reinitialize.
Should I?
Okay, no, I think it's okay. We can try like that.
You are not sending information, I think.
Are you sending information?
Are you getting it?
I think your hands move with me.
Yeah, they do.
Okay.
Let's try an object now. You can see now our same rubber duck, but on the simulation.
Can you show her this?
This is what she's seeing right now. We have a little less resolution than the real simulation.
Maybe show that she's grabbing it. Yeah.
She's lifting now the duck.
Are you holding it?
And she's like feeling some forces on the cage.
Okay.
Okay, so this.
We're gonna drop something in her hands.
Okay, next scenario is dropping an object on her hands. We get rid of the table.
Maybe not this one.
Maybe another one.
Okay.
That one looks better.
Yeah, maybe another. Yeah. Oh,
Now she's holding it. So yeah, of course, when she holds it, there are some forces applied to the sides, right? Because she's pushing inside the duck, and that's what she's feeling on the cage.
Yeah, there's a motor failure now. Okay.
So yeah, this is a quick demo of what our cage can do. Of course, as we mentioned, there are some issues and still a lot of room for improvement, but we can actually successfully apply forces when connected to the simulation.
Perfect. Does anyone have questions?
I have no questions, but just to say something, like mega job. Like this is awesome. I mean, to the team and Rafael, I'm like, this is like inner kid getting outside, you know, seeing some funny things and how it moves. Just awesome, guys.
Thank you very much. I totally agree. I think the team did an amazing job. I'm really happy.
Also, Susie, that's on the cage right now.
Yeah. Tribute to Susie for always being in the cage. Yeah, so yeah, that was our demo.
Thank you, guys.
Thank you. So, and of course, you have a robot camera as well, as you just saw.
Of course, this is the Roboy lab. We have many robots.
So does anyone have any other questions? Or so this is basically what we have from the Roboy finals. We are here to answer your questions. We want to discuss a bit more in depth certain aspects of it. Please feel free to ask. Otherwise, I would give back to Andre, and we will stay here. We can talk. So this is sort of concluding the official part of the Roboy finals. Yeah, thank you so much, everyone, for joining, and thank you, Andre, and over to you.
So thank you very much, guys. I'm asking again, are there any questions probably, so then we can give a chance for participants to ask their questions? Oh, okay, so I probably have a question. Speaking about scenario, controlling the robot on the Mars and letting them doing the heavy job, I'm wondering, are there any ideas? So you probably, as an operator, you don't really want to feel all the forces on you because then you will be tired. So my question is, are there any ideas how to decide how much forces to simulate, maybe to let the operator feel something, but not in a full extent, just a little bit? So are there any considerations how to deal with this kind of topics?
So this is a really interesting question about scaling forces. And frankly, we have not thought too much about it so far because the real challenge is actually, for now, still feeling the ones that are actually happening. But I can very well imagine that, like, that we'll have ways of scaling forces. Also, as you see, I mean, transparency is also for our attendants still an issue. I think that's one of the biggest thing we want to work on, is sort of getting a more predictive control, where we basically kind of understand when you're going to hit something and only then start applying forces. So keep the tendons really slack so you can move freely. And I think that's when, once we start being able to do this, we really also have a huge edge over all other kinds of systems, creating external forces, because you basically have full transparency, because you really don't feel it, right? So only when you really apply forces. And of course, I mean, you want to limit those forces at some point. Imagine the robot is hit by, I don't know, falling debris. Of course, we don't want to transmit these forces in full to the operator, also for safety reasons. Well, maybe one thing that will become interesting in this direction, but also further down the road, is really thinking about how can we display forces that we cannot display. So there's constraints on the whole overall system, such as like just the way the tendons are set up. You can't just display any kind of forces, but also you might have forces which are attacking to different body parts. How can we actually make it for you to feel that this force is applying here and not where we are applying the tendons right now? We're thinking of using potential soft exoskeletons to go in this direction. And this will be definitely some very interesting next steps in this direction, beyond solving the control issues that we're still facing right now.
Thank you very much.
And
yeah, sure, please go ahead.
No, I would have a question about autonomy. Do you have everything implemented for teleoperation, or is there something that is not mission critical and you want him to do it on his own?
That's an excellent question. So if you look at autonomy and where we stand right now in robotics in general, it's quite apparent that like any kind of complex interaction with the environment is just simply unsolved. Like we don't have, like, as soon as it's a one-off interaction in a complex chaotic environment, which is basically 99.9% of our world, like autonomy kind of starts to break apart and quickly becomes not reliable enough. I think the only thing that we can sort of say as humanity we have solved to a decent enough point so we can use it outside of something very defined like a factory is getting from A to B. And that also, and there also only if it's not with other cars on the same street. I mean, autonomous driving is still kind of largely, I mean, even Tesla and they are also struggling, right? They're kind of trying to find solutions. So I believe telepresence is really sort of giving us the opportunity to explore the potential of robotics and robotic bodies before we actually get to solve the autonomy. And I also believe this can be super helpful because this way of sort of also starting to understand the context these robots are going to work in before actually having to have solved the autonomy problem to bring those robots into these contexts. And of course, being able to I mean, then it is in the beginning for use cases, it's all about dull, dirty, dangerous jobs where we might be able to create some safety for users or create some time critical advantage through telepresence applications. So you don't have to travel somewhere, or if you can't travel as fast. And what I think is like the advantage over humanoid telepresence or versus other kinds of systems right now, you could use classical robotics, right, and teleoperated. It's really that what we are kind of projecting our understanding of our own body onto the robot. And I think this is a massive asset that is not to be underestimated, because once you have a non-humanoid morphology of the robot, remotely operating it becomes non-intuitive, because the human that operates it has to sort of make this transfer of understanding, and it's no longer something that's done by our like body control, but it's something we have to sort of transfer and actively think about, and gets harder. And you can show, like research shows that classical teleoperation, for example, with a joystick is about 100 times slower than a human can interact. And with telepresence, we can get much closer to human performance.
Absolutely, I agree. And if you teleoperate such a robot in, let's say, in situations like Fukushima, do you have any directions or ideas how you would protect the electronics, or is it not a scenario for Roboy?
So this is not a scenario that we care so much about. I mean, the vision of Roboy is kind of creating bodies like that are as close as possible eventually from functionality and to the human body. So the use cases we're looking are much more in the context of care, elderly care, home care, and so on, because in the care context, it actually matters how the robot looks. If you're going to Fukushima, there's definitely no humans, so it doesn't matter how the robot looks. What matters is that it's shielded from radiation and has some lead barrier and so on. But what I've seen so far from the community, this has proven to be quite a massive challenge. And a lot of the robots they've sent into those zones have just died in minutes. So it's absolutely non-trivial to create a robot that can sort of work in these high radiation environments because of the shielding.
One question I have, so as a robotics enthusiast, we like to think about the kind of global problems and try to figure out how to solve them. So could you please tell us about like a top 1 or 2 problems which are still open, which you are going to address, and which are difficult, where you know that it's not that easy to solve? Kind of
If you can win
strategical
10
problems.
million if you want by making a remote presence thing.
True. Do you mean like a top problem as a humanity problem, like climate change,
No, I mean,
or as a task, or
I mean,
a robot problem?
Related to Roboy, what kind of obstacles you're currently facing, which you're not really sure how to solve them?
Okay. So this is an excellent question, because I can basically, this is a very, very long list. So I think one of the major, I mean, so obviously we have to increase, we decrease latency, increase the resolution of the camera stream, increase like the fidelity of all our sensory streams. And but what I think is really interesting and sort of still largely unresolved is the whole haptic space. Like we're talking to a lot of those companies out there that are producing on one hand haptic devices or haptic sets, like sensor skins in a way, and on the other hand creating sensing gloves. And what you're basically having is you having when you display, so the problem with haptics is that our skin is a very annoying sense to stimulate, because it's super local. Like for camera, I just basically need to care for this here, but to stimulate touch, I need to basically cover the body with ways of stimulating these parts of the body for the operator. And of course, that's extremely tough to do for a lot of reasons. And so what's usually being done right now is, well, you just take care of sort of parts of the hand. You get some hand vibration and some force feedback of closing the hands, and sort of, it's a lot of it is focused right around the hands, because that's how you manipulate. But if you want to get to the point of like full body immersed experiencing the remote places, but also VR places, there is still a very long way to go in trying to understand how to work with the haptic on the haptic side. Also, because it's not only covering that, like our haptic sensing is not only covering our whole body, it is also 4 sensors crammed into one location, and they don't like to be. They're very hard to independently stimulate. Like, so you have temperature, pain, pressure, and touch sensing, and this is all sort of intertwined on your skin, and that makes the skin a really difficult to work with organ. And another thing that I think is really interesting is smell, because on one hand, again, our nose is this super complex chemical receptor that basically can figure out a lot of different chemicals from the stream. the air. But how do you measure it? So we have this problem that we have kind of impoverished sensing on one side, and on the other hand, we don't have good ways of stimulating, creating those smells and stimulating our receptors in ways that that it feels natural for you, and you actually feel the natural smell. Especially so. But what I believe is interesting and a big opportunity beyond the challenge is, and there's some really interesting research in this direction, is sort of creating some sort of robot synesthesia. Like, so there's been, for example, research to make you feel hot and cold by pumping capsaicin and menthol up your nose, which triggers a reflex for you to feel hot or cold, although this is purely basically stimulating some very local point in your body. And I think that's a very interesting sort of these kind of hacks that we can use, and I think a lot of research will have to go into these, simply because we kind of build full body stimulating devices that give you really this immersive feeling. Like if you think about just walking on sand, like also everything with the feet, this is completely untouched. There's no one is even caring for feet right now. I have not seen any kind of publications that are, how can we make someone feel if he's currently walking on sand, gravel? There's nothing. Like, it's not even done. So this is really this is a big space that is really, really underexplored, because it's just really hard, but super interesting, I believe.
Thank you very much. Are there any other questions?
Maybe for the remote present, is there a certain learning period that you say, okay, well, after you controlled Roboy for, I don't know, 3 hours, then you know exactly how this thing works. You are like pitch perfect, or does it take like a week, 10 minutes? How long before your body is the robot's body?
This is really an excellent question. And there's definitely a learning curve, and it happens on different levels. Like, so as you probably saw, the inverse kinematics of the robot is not perfect. So it doesn't actually perfectly track you. But if you use it long enough, you kind of understand how you need to move your arms so that the robot starts doing what it's supposed to do and you want it to do. So this, I mean, you learn quite quickly. So I would say it's actually quite similar, quite easy. Like you go into the thing, and after a few minutes, you kind of get a feeling for how to use it, and then I would say maybe after half an hour or so, you feel totally comfortable kind of using it to the level that you're able to get at this point. With more complex systems, like there's the TeleRobot, which is a haptic telerobotic system which is a collaboration between haptics, Shadow Hand, and SynTouch, which creates these sensors. There it's a bit more involved because it's a much bigger system, and it takes a bit more time, but it's also has a higher fidelity.
Cool.
Okay, so if there are no more questions,
I would have another question.
Oh, sure. Sure,
what are
go
your
ahead.
plans for controlling the fingers of Roboy? I mean, there are different systems, for example, for the glove to use the electric elastomere sensors, or maybe also like some sort of tendons, like with strings. Do you have any plans for that?
So in the past, we've been using the Sense Glove, which is a Dutch startup. They just released a second version, which is apparently a lot easier to put on. So we don't plan on developing something on our own, because that's actually quite an active space, because there's VR use cases for it. So there's at least 4 or 5 glove producers out there that you can work with. And so on the premium side, there's haptics, which has they can even sort of stimulate sort of parts of your finger, so so you feel something like rolling around in your hand, something like that, which is of course really, really cool. And then on the more primitive but useful side, because I mean for us we don't have a hand that can recognize this complexity, so I think we'll keep on working with the Sense Glove, which has basically force feedback. So if the robot grasps a cup, for example, and you can measure those forces, then we can translate these forces and apply them to the user, and also give you a small vibration feedback that you know that you should just currently are touching something.
Okay, I see. I also have another non-technical question. Does your team at the moment consist only of bachelor and master students, or?
No, actually, we sort of a core team of about 5 people that have been with Roboy for a long time, and most of them have been students before they're doing this full time as part of. So as I said, like we're working in collaboration with companies, and we're also doing writing research grant. We're kind of an independent research lab, if you want to say. And then for everything that you saw today, though, however, this was a student team, and these are all master students.
Maybe a small correction. So not everything that you saw today. I work at Roboy, so I also know. And so the control of the robot, the mapping between the movements was done before the students came. So they build on top of that. And one more addition. So if you want to work with an awesome robot, an awesome team, reach out to us. We always want to meet awesome engineers. And I think you can find us very easily on the internet.
Okay, thanks.
Good. So guys, any other questions? In this case, I would like again, thank you guys very, very much. This is really impressive. It's really amazing what you've just shows. It's a huge work, and it is of exactly an applause to all the students. This is really impressive, and I think you can be proud of what you achieve, and very nice presentation. So I'm just thank you very much. Thank you for letting us enjoy this presentation, and I hope to see a lot of interesting projects from you in the future.
Thank you very much also from our side, and really hope that soon we'll be able to do this meetup live, and then of course with the actual robots for everyone to see and try.
That would be extremely cool.
Yeah, we were so waiting for it. Like, yeah.
Okay, yeah. So thank you very much, and then have a nice evening.
Thank you. Bye bye.
Oh, yeah. Thanks.
Thank you.
Bye.
Bye.
Nice evening.
Goodbye.
Bye bye. It was awesome.
Bye.
Bye bye.
Thanks.
Thank you, Marisa.
Yeah, guys, congratulations. Very well done. Very good, very good.
It worked.
Very surprising.
Yeah, I thought to get you some views, but I don't want to, because then you would. But yeah, let's hope that soon we can barbecue something together and celebrate this closing of this loop and this.
Yeah,
that
would be nice. Something is missing without the barbecue at the end.
Yeah, right.
There's something missing. Roboy without barbecue is not Roboy.
Yeah, exactly. Okay, so we shut this down, I guess.
Okay.
Let's take the cage down.
Bye.
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 Did nothing.
Yeah, take the cage.
The motor is